Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video, I'm going to investigate how the Bertrand and Cournot models of oligopoly change when the firms involved have different cost functions from each other. In the previous few videos, I've gone through examples of both the Cournot and Bertrand models where all the firms had the exact same cost functions. We solved through the Nash equilibria and found that the Bertrand and Cournot models behave quite differently. That continues to be the case when we have different cost functions. Since it's the simpler of the two, we're going to start with Bertrand. I'm going to continue using the demand function, Q of P equals 320 minus 2P, which we've used in the previous few videos. We're still going to have two firms. Firm 1's cost function will remain 40Q1, but firm 2's cost function will now be 25Q2. This might be because firm 2 has access to superior production technology. Remember that in the Bertrand model, if one firm prices lower than the other, they take the entire market at that lower price, and if the prices are equal, then the firms split the market equally. When both firms had a marginal cost of 40, they always had an incentive to undercut each other, and so the only prices that could be a Nash equilibrium is both firms pricing at 40. Firm 1 is willing to bid the price down to 40, just like before. But is 40 and 40 still a Nash equilibrium? At that point, the firms are splitting the market. Firm 1 is making zero profit, but firm 2 is making a profit here, because their marginal cost is only 25. But could firm 2 do better? The answer to that is yes, because firm 2 can undercut firm 1 slightly, and go just under 40. Take the entire market, and firm 1 can't do anything about it, because if they try to undercut, they'll end up making a negative profit. And so our Nash equilibrium will be P1 equals 40, and P2 equals 40 minus delta, where delta is a very small number. If we think about this as an example with US currency, delta might be 1 cent. Here we're going to assume that delta is so tiny that P2 is effectively 40. That's just going to make the math a little easier. So this is going to result in Q1 equals 0, and Q2 equals 320 minus 2 times 40. Again, we could put the minus delta, but we're assuming the delta is so small that we won't even notice it. And so that's going to give us a quantity of 240. From here, we know that the profit firm 1 makes is 0, and the profit firm 2 makes is going to be price of 40 times a quantity of 240 minus a total cost of 25 times 240, which is going to be 3,600. We can see that this is a lot better than the 0 that everybody was making when they had equal marginal cost. So to sum up, in the Bertrand model, when one firm has a lower marginal cost than the other, they are able to take the entire market by undercutting slightly below the other firm's marginal cost, and they're going to be able to make a positive profit in doing so. Now let's look at the Cournot model. We are going to continue with the same example. C1 of Q1 equals 40 Q1. C2 of Q2 equals 25 Q2. As before, the demand function is Q of P equals 320 minus 2P. And as always, what we always want to do when we start a Cournot problem is flip this thing around to get our inverse demand function, P of Q, which in this case is 160 minus Q over 2. Plugging in the little q's, that gives us 160 minus Q1 over 2 minus Q2 over 2. We're going to go through things just like we did before when we had equal cost functions. Since firm 1's cost function is exactly the same to the cost function that we used 2 videos ago, I am not going to go through that again. I'm just going to do firm 2's. So first we set up the profit function. We have price times quantity for the total revenue. Price is 120 minus Q1 over 2 minus Q2 over 2, given by our inverse demand function, times the quantity of Q2 minus the total cost of 25 Q2. Then I'm going to multiply this out to get 160 Q2 minus Q1 Q2 over 2 minus Q2 squared over 2 minus 25 Q2. Collecting terms, I can take 160 minus 25, which is 135, and then just get rid of this. That's going to be our profit function. Next, we're going to take the first order condition for firm 2. To do that, we're going to take the partial derivative of pi 2 with respect to q2, which will give us 135 minus q1 over 2 minus q2. Again, the squared comes down, and that's going to cancel out the 1/2. And of course, we set that equal to 0. Add q2 to both sides to get our best response function for firm 2. 135 minus q1 over 2. As I mentioned before, firm 1's best response function is going to be exactly the same as the one we found before because their cost function is still 40q1. And so, just to remind you what that is, we had q1 squared equals 120 minus q2 over 2. From here, we need to do the algebra to solve for our Nash equilibrium. I'm going to take firm 1's best response function, q1 equals 120 minus q2 over 2, and I'm going to substitute in firm 2's best response function for the q2. So that's going to give us 135 minus q1 over 2, and all of that divided by 2. As always, remember to divide the entire thing by 2. Again, there are many ways to go about this, but I'm going to multiply everything by 2 to get rid of that fraction. So that's going to give me 2q1 equals 240 minus 135 minus q1 over 2. That's still in parentheses, so now I'm going to distribute the minus sign. So we're going to have minus 135 plus q1 over 2. Again, be very careful about distributing these minus signs. Subtract q1 from both sides is going to give me 3/2 q1 equals 240 minus 135, which is 105. And that's going to give me a Cournot equilibrium quantity for firm 1 of 105 times 2/3, which is going to be 70. Then I can plug that back into firm 2's best response function to get firm 2's Cournot equilibrium quantity, 135 minus 70 over 2. 70 over 2 is 35, and that's going to give me 100. At this point, notice that the two firms are no longer producing the same amount of output, like they were when the cost functions were the same. This also means we can't use the symmetry shortcut when we have different cost functions. Further, notice that the firm that has the lower cost, firm 2, who has a marginal cost of 25, ends up producing a larger quantity than the firm with the higher cost, firm 1, who had a marginal cost of 40. That's always going to be the case. From here, we'll plug everything in to solve for the price and quantity. As always, there is a single Cournot equilibrium price, unlike in Bertrand. To get that, we're going to plug our quantities into our inverse demand function. 160 minus q1 over 2 minus q2 over 2. And so that gives us 160 minus 35 minus 50, which comes out to 75. Now to figure out the profit that each firm makes. For firm 1, we've got price times quantity minus total cost, 40 times quantity, so that's 70. That comes out to 2,450. And for firm 2, we've got, again, price of 75, but this time a quantity of 100, minus a total cost of 25 times a quantity of 100, and that's going to give us a total profit of 5,000. And so what we see here is that the lower cost firm, firm 2, ends up making a much higher profit, in this case slightly over double of the firm with the higher cost. But it's not as big of a difference as in Bertrand. This is because in Cournot, the lower cost firm can definitely take advantage of its lower cost by producing a higher quantity, but they're unable to completely undercut the other firm and lock them out of the market entirely. Firm 1 here is still making a profit, but not nearly as much profit as firm 2 with the lower cost. And that is everything for the basic oligopoly models for now. In this set of videos, we have solved for Nash equilibria in the two basic oligopoly models, the Cournot model and the Bertrand model. As we've seen, the simple assumption of whether firms choose quantities and let the market determine the price, as in Cournot, or firms choose prices and let the market determine the quantities, as in Bertrand, makes a huge difference. But in both cases, we have found the Nash equilibrium where both firms are best responding to each other. And in doing so, we've found a result similar to the prisoner's dilemma. The profit that they make in the Nash equilibrium is lower than the profit that they could have made from cooperating. To enable a cooperative outcome, we are going to have to enrich the model, and that's where we are going next. But that is all for now. If you have any questions, feel free to let me know. Thanks for watching.